Okay. So let's generate Bernoulli random variables. Okay. So can I mean, I just wrote something here, but can somebody give me a value for so the Bernoulli random variable has a parameter. Okay. So let us say that so can somebody give me a numerical value for the parameter the p?
5/9.
Okay. Uh, okay. 5/9. Uh, let's also do a parameter we can think about a little bit easily. Give me a simpler fraction. We can do with this, but maybe we'll change it when it comes to that. Okay. Now what we'll do is this. Okay. So now if I generate a Bernoulli p random variable. Okay. Right. So now this. Okay, we have been doing 0 and 1, so I'll do it accordingly. So, okay, uh, so this is 1 bit. If I generate it again, okay, and so on. Okay, so I can generate, so every time I run this code, I'm generating a bit. Okay, so 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 I get a 0, I get a 1, I get a 1 again, I get a 1 again, I get a 1 again, and so on. Okay, so let's see what happens when we generate like a sequence of them. How many bits do we want to generate independently? Okay, let's say we generate 10 bits. Okay, so let us say we generate 10 bits. How do you think the sample will look like?
Slightly more ones than zeros.
Okay, so this is one example. Okay, so let's generate 10 bits again. In this case, 1, 2, 3, 4, 5, 5 zeros and 5 ones. Okay, I'll also just count the, so instead of us counting, okay, so it's also possible we get something like this. Okay, I was going to see how long before, but this is a question I'll ask you. Okay, it's also quite possible that I see a sample with very few ones. Okay, it's actually also possible I see a sample with no ones. Okay, so what sort of a so is everyone clear on this? Every time we generate a sample, okay, the number of ones is random. Okay, the fact that p is 5/9, okay, uh, does not uh, does not imply that the number of ones will always be greater than the number of zeros. Okay, it could be greater, it could be smaller. What matters is only the probability with which they are generated. Okay, and in fact, if you take smaller samples, okay, if I take 5 samples, okay, it's quite likely that I get many more cases with very few ones. Okay, in this case, like p is this one, but it's quite possible that I get very few ones within my sample. Okay, it's also this. This is very lucky. Okay, it's also possible that I get everything to be 1. Okay, so an individual sample can have the number of ones anywhere between 0 to 5. Okay, or anywhere between 0 to n. Okay, so everyone okay with this? Okay, so what sort of a random variable is the number of ones here?
Would be just Bernoulli 5/9.
Each individual bit, okay, so each of these individual bits is a Bernoulli finite random variable, but the total number of ones, okay, so here it says 5 ones, this one, okay, how many ones are there in the sample? What sort of a random variable is that? Okay, uh, what is the number of, what sort of a random variable is that? Yeah, it's binomial, and it has that's it, right? So the number of ones in the sample is a binomial random variable, okay, with parameters n and p. Okay, so does this? So everyone okay with this?
It's binomial because each of them are independent.
Right. So we are. So technically, when you use all of these, right? When you use like computer simulations, okay, we cannot generate truly independent bits, okay, but so here, like, so that is a, that's like a that's something that happens when, because we are trying to do a simulation, okay. uh, what happens here is that the way the programs are generated, these random numbers are not truly random, okay. So the 5 bits that we have generated on the computer, okay, they are made to simulate independence, okay. So they are made to simulate independence, but they're not truly independent, okay, because computers, like the way we do it, they're kind of deterministic, okay. So we can only go so far, okay, but for the purposes of this class, to the first order, okay, we can assume that they are independent. Okay, so let's do something like this. Let's take n to be an even number. Okay, okay, so let us say that. Okay, so when we are going to look at pairs of bits. Okay, so we are going to look at pairs of bits. So here, the pairs of, so we are going to break it down into something like this. Just a second. Just means. Okay, right. So I'm going to see pairs of bits here. Okay. Okay, so here, like this sample, what I've done is I've taken the first two bits. The first two bits is in the first row of this matrix. Okay, the next two bits, 1, 1, it's in the second row of this matrix. Okay, the last two bits is in the third row of this matrix. Okay, how many times do I expect to see each one of them? Okay, let's use a slightly larger sample. Okay, so now this is a sample with 20 ones, okay, and sorry, sample of size 20. Okay, so there are 20 independent Bernoulli random variable, 20 independent bits. Okay, now the sample has 11 ones. Okay, what I've also done is I look at pairs of bits. Okay, so 1, 1 appears 1, 2, 3, 4 times. Okay, 1, 0 appears 1, 2, 3 times. Okay, 0, 0 appears a few times, 0, 1 appears a few times. Okay, how many times do I expect to see each one of them? Okay, can you calculate this and tell me? Okay, so it is okay. So let me restate that. Okay, so here, like I'm looking at the number of times the consecutive bits are equal to 1. Okay, the number of times the consecutive bits are equal to sorry, the number of times the consecutive bits are 1, 1. Okay, the number of times consecutive bits are 1, 0. Okay, and so on. Right? Does that make sense? Right? So I'm taking the first two bits, they are 1, 1. Then I'm taking the second and the third and fourth bits, they are 1, 0. Okay. The uh, fifth and sixth bits, they happen to be 0, 0, and so on. Okay. So I'm splitting the string into bits of substrings of length 2. Okay. Now, there are only 4 possible substrings of length 2. Okay, the substring has to be 0, 0, 0, 1, 1, 0, or 1, 1. Okay, what to let's pick any one. Okay, let's take the sequence 1, 1. Okay, how many times do I expect 1, 1 to appear?
Would it be the probability p squared times n over 2?
Very good.
Yes.
Very good. Right. So there are, so what happens now is, so yeah, you're absolutely right. So what we are doing is like we are just looking at a sequence of independent random variables. Okay. Now we know that the probability of 1, 1 is p squared. Okay. Because the bits are independent, the probability of 1, 1 is p squared. Okay. And if we ask how many times will 1, 1 appear, okay, among the rows of this matrix, okay, there are exactly n over 2 rows, okay, and whether 1, 1 appears in a row is an indicator random variable, okay, where it is 1, 1 with probability p squared. Okay, so there are n over 2 samples. So we think of it as n over 2 samples. Okay, and each sample can be 1 with probability. Each sample can be 1, 1 with probability p squared. Okay, since there are n over 2 samples, the expected number of ones is n over 2 times p squared. Okay, is everyone okay with this? Okay, so what is the expected number of rows, which will be, let's say, 1, 0.
So it's still kind of like the same thing. It's p times the probability of 0, so 1 minus p. So p times 1 minus p times n over 2.
Okay, very good. So you'll have n over 2 times, okay, the probability of 1, 0, it's p times 1 minus p. Okay, so does this, so is everyone okay with this? Okay, but suppose I did a funnier thing. Okay, okay. So writing it in code is a little tricky. And this 1 second. So let's do it a little bit differently. Okay, same thing. I do these things a little bit differently now. Okay, I do things a little bit differently. So what I've done here is the following. So where is this thing? Okay. Right. So same sample. I mean, like not same sample. So I have a sample here. Okay. Now what I do is I take the first two bits of the sample that goes into my first row. Okay. I take the second and third bits of the sample. Okay. Put it in the second row. The third and fourth bits of the sample, put it in the third row, and so on. Right. So everyone sees what is happening here. Okay. Same question. What is the expected number of rows which will be 1 1, and what is the expected number of rows which will be 1 0? Okay, now you see, right, like, so the difference between this case and the previous case is, in the previous case we took these two bits as the first row, then we took these two bits as the second row. Okay, now we know but that because these bits are independent. Okay, in the previous example the rows were independent. Okay, the rows of the matrix before were independent. Okay, not so much the situation now. Yeah, so the, yes, so the rows, the first and second row contain the same, they both contain x2. Right, so we have n minus 1 pips. Okay, so the first and second row both contain the bit x2. Okay, so they're not independent. Okay, but what is the expected number of rows that will be 1 1? Okay, so how do we do this?
Like the first variable would be the only independent one, right?
Right,
But
so,
then
so like I call this matrix W right now. Okay, so let's say W is something like this. Okay, so in right? So W is this matrix. W has, I think here it is N is 20, right? So W has 10 rows. Let's use a smaller number for now because we are just figuring out, right? So if N is 6, okay, so W has 3 rows while Z has 5 rows, okay? The difference here is that the rows of W are independent, okay? The rows of Z are not independent. Does everyone see that? Okay, so the first question was, what is the expected number of rows of W which will be 1, 1? Okay, and you told me the answer was N over 2 times P squared. That's absolutely right. Okay, now the question is, what is the expected number of rows of Z which will be 1, 1?
So would you start by listing like a conditional probability, say like if we represent each position as like k, the probability that k equals 1 given that the previous number k minus 1 is equal to 1, and then start like working with that to get it into conditional times the prior, kind of that form, and we could work with it that way.
So we could write the conditional probabilities, that's true. But my claim is that there's a much more simpler way to think about this. The answer is much more simpler. It's something that I could expect you to do mentally. So, right? So remember that here, how did we get this? Okay, we saw, we said, okay, we are thinking of this indicator. Okay, so an indicator that any of the rows is equal to 1, 1, right? So, and we looked at this indicator and we said, okay, the probability this indicator equals 1 is P squared. Okay, and then there are n over 2 rows and expectation is linear, so it is n over 2 times P squared. Okay, now the exact same argument will still apply. Okay, because linearity of expectation holds even when your random variables are not independent. Okay, so it is true that the rows are no longer independent. Okay, in fact, you know that, for example, you know that if one of the rows is 1, 0, okay, the next row definitely is not 1, 0, right? Because the next row has to start from a 0, right? So you know that this indicator that each row is 1, 0, it's not independent of the indicator that the next row is 1, 0, okay? But the fact of the matter is it does not matter, okay? Expectation is linear. Okay, the probability any individual row is equal to 1, 0 is P times 1 minus P. Okay, now that means even though these rows are not independent, the answer here will look very similar. Right, so here the answer is n minus 1 times P squared, and here the answer is n minus 1 times p times 1 minus p. Okay, right? So this is because, okay, let zi be 1 if pi, okay, okay. So define these random variables. Okay, so we want the number of rows which are okay. So the expected number of rows, and we'll call this n. I don't want to type so much. Okay, is the expectation of z1 plus z2. Right, and this we know is the expectation of, right, and this is just the, does everyone see this? Right, so this kind of tells you how, I mean, like when you so the fact that expectation is a linear operation, okay, it's actually a very, very, very powerful principle. Okay, so it actually does not even matter how these random variables are related. Okay, the expectation of the sum of random variables is always the sum of expectations. So when you are speaking about expectations, you can often answer a lot of questions very easily. Okay, and so is this, so is everyone okay with this? Okay, so any questions? Okay, so when I give you the code, I'll also let you run samples of any size where you actually count the number of rows, which is 1, 0, 1, 1, and so on. Okay, and you can see for yourself that this is true. Okay, but also, like, do we understand, like, so also, do we understand, like, how to do, would you be able to compute, for example, what is the probability z2 is 1 1 given z1 is 0 1? Okay, what's the probability z2 is 1 1 given z1 is 0 1?
Would be p.
Uh, very good. Okay, but that's very good. But how do you compute this?
The second the second number in z1 is going to become the first number in z2,
That's
and
excellent.
so that probability is already sealed. That's like 1, then it's just times the other probability, so p.
It's excellent. So this is exactly the intuition that we want to develop. So if you want to do it formally, right, you would say this is the probability z1 is 0 1 and z2 is 1 1. Okay. Uh, uh, okay, divided by the probability z2 or z1 equals 0 1. Okay, but now if you write it according to the probabilities of x, this is x1 is 0, so this is the probability x1 is 0, x2 is 1, okay, and x3 has to be 1 as well, okay, divided by the probability that x1 is right? And this is just the probability x3 equals 1, okay, which is p, what Caleb said. Okay, right? So make sure that you're able to see these computations. Okay, so is everyone okay with this? Okay, so good. Let's maybe we do a little more of this. Okay, so let's look at the binomial random variable. Okay, so the number of ones in a sample. Okay, so what I'm going to do is like I'm going to pick. I'm going to just remind ourselves n is 6. Okay. Right, so I've done the same thing. Okay, so n is 6 and I've printed here the number of ones. Okay, so each time, so now we are only focusing, I mean, we could also print the sample, but we are going to remove this because we are, right? So here, like for now, I'm keeping the sample as well. The sample is, so this is the sample, okay? The sample is all zero, so the number of ones is zero, the sample, okay, is 1 0 0 0 0 1, so the number of ones is 2 and so on, okay? So, but right now, we won't worry about the sample, okay? We are only focusing on the number of ones in the sample, okay? Now, if I take, okay, so in this sample, I have 2 ones, okay? In the next sample, I have 5 ones. In the next sample, I have 3 ones, and so on. Okay, so the experiment is that I draw a sequence of 6 independent Bernoulli random variables, okay, and I count the number of ones in the sample. Okay, now I perform this entire experiment many times. Okay, I'm going to perform this entire experiment. Let us say, how many times do you want me to do this?
And do like 100.
Okay, okay, I'm going to perform this entire experiment 100 times. Each time, right? So in the first time I did this, first time I drew a sample of 6 bits. I got 2 ones. Next time I got 3 ones. Okay, next time I got 2 ones, and so on. Okay, so everyone completely okay with this? Okay, then 3 ones, then 5 ones, and so on. Okay, so this is the outcome of 100 trials. Okay, each trial involves taking a sample of length 6, okay, and counting the number of ones. Okay, now if I draw a histogram of this, okay, so I count the number of times I see a 2, I count the number of times I see a 3, count the number of times I see a 0, and so on. Okay, if I draw the histogram of this, okay, so let me do that. I get something like this. Okay, so actually, like the bin, uh, so it is, okay, so let me make this a little cleaner. Okay, so this is like the right. So I just make the picture a little bit cleaner. Okay, so this is the histogram. Okay, so 100 trials. Okay, the number of times. So this value says the number of times we saw a 0. This tells us the number of times we saw a 1. This tells us the number of times we saw a 2, 3, 4, 5, and 6. Okay, so this is so, but how do I get the proportion? Okay, so suppose I want to check the number of times I got y equals 3. Okay, so in 100 trials, right? So the number of times I get y equals 3, right? So that is this. It's somewhere in the ballpark of 30. Okay? Uh, so what is this? What is the expected number of so the expected number of times I get 3 ones in a sample of size 6. Okay, what is this? What is this expectation?
It'd be like p cubed times n.
Let's be okay. So not P2. So this is 100 times the probability that y equals 3. Okay. So let's go step by step. You have 100 trials. Okay. Why is this binomial random variable? Each trial you do an observation of this binomial random variable. Okay. So it's 100 times the probability y equals 3. So this is exactly the probability that we see 3 ones among 6 bits when we do this experiment 100 times. Okay, so what is the probability y equals 3?
So it'd be the probability of seeing 3 successes in 6 tries. So it'd be p cubed, and then the probability of the failures, 1 minus p cubed.
There's something else. There's something else, right? So you're right that any single sequence that has 3 successes and 3 failures is this. This is any single sequence that has 3 successes and 3 failures. But how many times could you have 3 successes and 3 failures? Right, so this is a sequence of length 6. 3 of those bits are 1 and 3 of them are 0. How many different ways? Yeah, it is 6 choose 3 of these sequences. Right? So this number is close to 100 times 6 choose 3 times p cubed times 1 minus p cubed. Okay, let us see what happens when we increase the value for n. Right, so when we increase the value for n, okay, this is not really typical. Right, so when we increase the value for n, okay, you're going to get another this one. This time the peak is near 5 over 9, closer to 5 over 9. Okay, So actually we are probably running out of time. But what I want you to do is I'll give you this. How many of you know how to run these Python notebooks? It's relatively simple. Like you can change the code. You can fiddle around with the values. You can just rewrite the values anywhere here. Okay. And you just enter these. You just type enter. You just need to have something that you can run Python notebooks in. Okay. So if you have a Python installation working, okay, this should be relatively easy. And I'm pretty sure like there may be a way to run this online. Does anyone know? Does anyone know if there's a website that allows you to upload a Python notebook and you can run it online? It's something that really should be there. Like I'm pretty sure it is there, some variation of this. Okay. So if you have a Python setup already and you can run Python notebooks, play around with these values, okay, and see what happens. Okay. Try to come up with different kinds of experiments. Okay. And we'll continue next class. Okay. So any questions? Okay. So I think one of you mentioned that Kokan. Okay, so I'll look it up. I'll let you know if I find something online. Caleb, but I'll probably ask you for more details on this. Okay. If I find something that allows you to do this online, so that way you can run this even if you don't have a Python setup on your computer. Okay. So just play around with it and ask me questions, ask me to do things on this setup, okay, and see what will happen. Okay, so it's important to, so this setup captures a lot of what I mean, not just a lot, captures everything about random variables that we have set so far. Okay, so it's kind of important that we understand this well. Okay. Okay, so I'll see you on Monday. But I'll stop recording. But if you have questions, you can continue asking.